I'm Zor. Welcome to Unizor Education. I would like to continue to talk about rational numbers. Rational strings will be subject. When I was introducing integer numbers, besides something which is, I would say, a homemade definition of -3 as the number which, if added to 3, results in 0. This is not a mathematically rigorous definition, because maybe there is no such thing as -3, which will result in 0 if added to 3. So instead, I have offered a string-based notation. I have basically constructed new objects which looked like 4 plus 3, and defined operations of addition among them, and it actually followed that in that particular universe of integer numbers, which I have built using these abstract strings, I can basically do all the arithmetic operations. That was fine for introducing an operation of subtraction, and now integer numbers are complete, because operation of subtraction is defined on any two numbers in as much as operation of addition was defined only among the natural numbers, but all of them. Now, we have similar situation when we are introducing rational numbers. These were introduced as a result, as a necessity, to be able to divide any two numbers into each other. We know that we can multiply two integer numbers, but we cannot always divide one by another. So if I'm saying that I can multiply 3 by 5, that's no problem, but if I want to divide 3 by 5 among the integer numbers, that is not possible. So to overcome this, again, homemade definition was, okay, we introduce number 3/5, which if multiplied by 5 gives 3. Well, it's not good enough for definition, because maybe there is no such number as 3/5. We just, we say a property of an object is defining an object. That's not necessarily true. Sometimes you can define the property of an abstract object when it doesn't exist at all. To constructively approach this particular problem is to basically create new objects from whatever elements you have. And in as much as I created integer numbers using these strings we were talking about with curly brackets, curly braces, whatever, I will try to do very much similar thing to introduce rational numbers. So, if these are integer, instead of expanding the set of integer numbers into a set of rational numbers, I'm saying that rational numbers will be a completely different set. However, there will be a subset which we can call pseudo integer. This is the subset. And every element of integers, every element of integer set, every integer number, should have a corresponding element among pseudo-integer numbers, which are part of subset of rational numbers. And operations among integer numbers, like multiplication in our case, and division whenever it's possible, should really correspond to the similar operation among the pseudo-numbers. So that's the goal. And let me start walking along this way, and I will constructively introduce the rational numbers by basically saying, okay, these are new objects which I'm going to construct. They are called rational. Okay, so here is the definition. Rational numbers are strings of curly braces, and in between you have two integer numbers separated by vertical bar. Well, obviously you understand that in the future we will probably write something like this, which is much more traditional, but I would like to break this tradition because this is a formal definition. Our rational number is not a number, so to speak, it's a string which consists of two braces on both sides, vertical bar in the middle, and two integer numbers on the left and on the right from the vertical bar. Alright, so I have introduced these numbers, and now I have to operate upon them. So I have to define an operation of multiplication, because that's basically the ultimate goal, to operate future numbers freely as far as multiplication and division are concerned. So let's define an operation of multiplication. Well, there is one more thing which I actually did not say yet. And should not equal to 0. This is part of the definition. So my new set contains all strings of this type where n is not equal to 0. And obviously you understand that you cannot divide by 0 for whatever reasons. And that's why I have restricted my constructed number of constructed objects to those where denominator, I will call the denominator and numerator obviously in the future, where denominator is not equal to 0. Okay, so these are strings, nothing more than that. So first what I'm saying is that there is one particular string which is 1 over 1, which is a unity. Unity means that being multiplied by any other rational number in this particular incarnation as a string, it will result in the same string. So if I will do, I'm introducing an operation of multiplication. So this is a multiplication. If I am doing something like this, I will always have this, and vice versa. Vice versa means I'm basically defining the commutative law in this particular case. So that's the definition of the unity actually is. If multiplied by anything else, it will result in the same, that same anything else. Left to right or right to left. Okay, so this is one thing which we have defined by definition. So this new set of elements where m and n are any numbers, any integer numbers, one of those is this particular element. So I'm saying that this is it. This is the unit which will result in this rule of multiplication. Another thing which I would like to say, again by definition, is by definition that if you have two rational numbers, rational string, whatever you want to call it, of this type, where m is any integer number, this will be a unity. What this basically means is, well, obviously, as you understand, in the future, an integer 123 will correspond to a pseudo-integer 123 over 1. So this is 1 over 123, which is an opposite number, result of the multiplication of 123 and 1 over 123 should be equal to 1. So by definition, I actually say that this is the rule of multiplication of my numbers. My new numbers, my new rational numbers, which are actual strings. So for any number of this type, there is always an opposite of this type. Okay. saying that, I have to really introduce the rule of multiplication between two rational numbers as introduced here. And the rule is very simple. If I have a over b and I'm multiplying c over d, where a, b, c, d are any integer numbers, by definition this is the result of multiplication of a by c, and we know how to multiply two integer numbers. That would be my numerator, and my denominator will be b times d. So this is the real multiplication, and this is the real multiplication between two natural numbers. So that's how I define my multiplication between two rational numbers. I multiply numerators and I multiply denominators. This is a rule, this is the definition of multiplication between two strings, which represent my natural numbers. Well, as a consequence of this, let me just prove a very simple property of these numbers. You know that if you have a fraction, let's say 4 over 8, you can always reduce it to 1/2. So if there is a common multiplier in numerator and denominator, you can basically reduce the fraction to get a smaller numbers in both numerator and denominator. So let me do something similar with this. My property which I would like to prove is the following. Let's assume that there is a common denominator between common multiplier k, which is included in numerator and denominator. I would actually like to prove that this is the same as m over n, so that this string is equal to this string, using these rules. Okay, how can I prove it? Well, very easily actually. I will use just these two rules, basically. And here is how. I can say that this particular rational number, expressed as a string of this type of quality, is equal to result of multiplication of m over 1 times k over 1 times, this is multiplication of rational numbers, 1 over n times 1 over k. Well, why is it? Well, obviously, if you multiply m over 1 times k over 1, according to this rule, m over 1, k over 1. It will be mk over 1, 1. So this will be mk over 1. And this, similarly, will be 1 times 1, over n times k. And the result of multiplication of these two will be mk times 1 on the top and 1 times mk on the bottom. So that's why I can do this. But now, considering I have defined my operations in such a way that obviously I would like to say that all the commutative and associative laws of multiplication should be preserved, basically I can use the commutative law and and change the order of these two things. So instead of k over 1 and then 1 over n, I can put 1 over n first and k over 1 second. That's just the result of the commutative law, which should be part of the definition. Now, here, using dissociative law, I can say k over 1 and 1 over k. That results in, according to rule number 1, k over 1 and 1 over k, that's 1 over 1, right? So I can say that the whole thing is equal to m over 1 times 1 over n times, and these two guys will give me 1 over 1. Now, multiplication by a unity actually results in the same number I started with, so I can just completely wipe out this multiplication by 1 over 1. And this thing, again, using this rule, is equal to m times 1 on the top, which is m, and 1 times n on the bottom. Well, a couple of lines of proof basically shows that we can reduce our rational number by the common multiplier. So that was basically the purpose. Now, as you probably have guessed correctly, all I have to do is to put into correspondence my integer numbers and my new rational numbers. So again, these are integers, these are rational numbers. This is a subset of pseudo-integer numbers, and I have to build the correspondence, but in such a way that if I have image of one integer number as a pseudo-integer, and I have an image of another integer number as a pseudo-integer, then the result of the multiplication of these two integers should map into the result of the multiplication of their images, pseudo-integers. Otherwise, this correspondence is not really well defined. Well, obviously, any integer number n will correspond to, as you understand, a rational number, a string which contains 1 as the component on the right from the vertical bar. Similarly to the fact that 5 over 1 is actually 5, right? So that's the correspondence, and obviously there is a one-to-one correspondence between all integer numbers and all rational numbers of this type. Now, how can I prove this type of correspondence? Okay, let's take number n, which maps into rational number n over 1. Now, result of their multiplication here is m times n. Result of the multiplication of these two things, it's premature, result of multiplication of these two things, according to the rules, is, you remember, numerators should be multiplied by themselves as two integer numbers, and denominators should be multiplied as integer numbers. But this is 1, obviously, right? 1 times 1. And this is exactly what should be expected from the image of the mn. So mn maps to this. So either we do it this way, so we multiply and then map, or first we map and use the images and multiply according to the rules of the multiplication of rational numbers, we get exactly the same thing. So that proves that our representation of rational numbers in this way allows a very well-defined mapping between integers and a subset of the rational numbers, which we can call pseudo-integer numbers, and this correspondence is really well balanced, etc. But now, what's the advantage of introducing these numbers? Well, obviously, now we can divide anything into anything, and this is basically how. We can introduce operation of division I'm introducing operation of division. If I have rational number AB and I have another rational number C over D, and if you remember, neither B nor D are 0, then I can define operation of division between them as operation of multiplication by reverse of this particular number. And what is the reverse of C over D? Well, it's D over C. Which, by the way, indicates that C also should not be equal to 0. Otherwise, this division is not defined. Now, why CG reverse is GC, as I was saying? Well, for a simple reason. If you will multiply CG times GC, this is CG over GC, and you know we can reduce the rational number by the common multiplier, and common multiplier is CD, obviously, so this is the same thing as 1 over 1, which is a unity. So if the result of multiplication is unity, that's what we call that one is a reverse of another. Alright, so this is a definition of the division. And as you see, any two rational numbers, as long as B, C, and D are not 0, can be divided one by another. Now, going back to the integer numbers and pseudo-integer representation of our integers among rational numbers, what we can say is that 123 over 1, which is actually 123 in integer number. If you will multiply it by 123, you will get 123 times 1, 123, and 1 times 123 again 123, which is reducible to 1 over 1. So we have two different numbers which, if multiplied, result by 1. What does it mean? It means that this number, 1 over 123, can be called an inverse of original number 123 over 1. So if among the integer numbers you cannot find anything which is an inverse of 123. Among these rational numbers, it's very easy to do. You just change the order of left and right part in this string representation, and you got a new number which serves as an opposite, as a reverse of the original number. Well, that basically concludes introduction of rational numbers using these strings. Now, what's the advantage? Let me just emphasize it again. I have constructed rational numbers. I'm not saying that, well, let's introduce a number which, if multiplied by 123, gives 1. This is not the proper definition, because maybe there is no such number, and if there is one, we have not really defined what's the operation of multiplication among them. So who knows? In this way, I have basically constructed a new set of objects, which is a set of strings representing rational numbers, if you wish, this type. And among these strings, I can very easily define this operation of division or a reverse element to anything in very defined and constructive way. So that's what's very important. This is a constructive approach which allows to basically say, I'm not defining some abstract object which has certain properties. I'm saying this is an object and these are the properties. So from the strict position, it has much more weight. And that was the purpose basically of this lecture, to satisfy those people who feel that definition of 123 reverse as just the result of a multiplication of some number which gives 1, that this type of a definition is really light-weighted. This is much more rigorous, and it's definitely not the only one which people can use to more or less rigorously introduce the rational numbers. But that's just one of those approaches, and the one which gives you at least some positive feeling that certain level of rigorousness is really needed, and this is the way to basically achieve it. Thanks very much. I'm Zor. Welcome to Unizor Education. We have already spoken about rational numbers and their more formal introduction by using rational strings of the form where m and n are two integers. Basically, this is just a formal introduction. In the real life, we're using slightly different notation, but I wanted to stick to this formalism and further define arithmetic operations with rational numbers. Basically, we have defined rational numbers in this formalism based on pure expansion to these strings, the regular laws of multiplication of integer numbers. So if you remember, these are representing actually numerator and denominator of the rational fraction. But in any case, right now we are about to define some other operations which are possible with rational numbers. First of all, very briefly, what we have defined as operation of operations available with these numbers are the following. If you remember, there is a number 1 which plays the very important role that multiplied by any rational number, it basically results in exactly the same one. Another operation which we have defined was an operation of multiplication. When we have two different rational number and multiply them, we will get A, C, B, D. This is just a definition of the operation of multiplication on these formal strings. So forget about the real multiplication as you know it in the realm of rational numbers. This is just a completely different approach with strings. A and B and C and D are integer numbers which we can multiply. So based on these, the multiplication laws of integer numbers, we have defined the operation for rational. And obviously we introduce it in such a way that operations, that the laws of commutation and association will be observed. So you can change the order of multiplication, it will be the same, or if you have three different strings which are multiplying by each other, the sequence is not really important. Okay, this is just a brief repetition of whatever it was before. Now let's continue moving forward towards other arithmetics which we can do with these rational strings. Let's call it rational strings, it's a nice name. Okay, So first of all, I would like to talk about reduction of these strings. Reduction, I mean, is the following. Let's consider the integer m is a result of the multiplication of two other integers, and integer n is the result of multiplication of these integers. What it means is that the k is common multiplier, common factor, if you wish, for m and n. Simple examples are 6 and 4. 6 is 2 times 3 and 4 is 2 times 2, which means that the 2 is common. So I'm trying to approach the problem of reducing the rational number, something like, in this particular case, if you have 6/4, we know that this is 3 seconds, right? So I would like to formally introduce this type of operation. So to do that, I actually have to prove that the rational numbers uppercase m over n and lowercase m over n are exactly the same. So if k is common factor, common multiplier in both numerator and denominator, then I can reduce by k, and what's left is whatever the results of the division, capital M by k, which is m, and capital N by k, which is lowercase n. So how can I prove that? Well, very easily. Since I know that capital M is lowercase m by k, I can put it here. Same for n. Actually, I have a little bit more room for this. Okay, that's what I have. So how can I prove that? Well, very easily. As we know, the operation of multiplication among these rational strings was defined in such a way that m over k and k equals to mk1 times 1 over mk. So instead of m times k as denominator and n times k as numerator and denominator, I'm writing the multiplication of these two rational strings. In this case, numerator is the same as this and denominator is 1. And in this case, numerator is 1 and denominator is this one. Well, indeed, the multiplication law of these two rational strings states that I have to multiply numerator by left hand by left hand, right hand by right hand of the vertical bar. So m times k times 1 will be on the left of the bar, and 1 times n times k will be on the right, which is n times k, will be on the right of the bar. So this representation is perfectly lawful without any problems. Similarly, m times k over 1 I can represent as m over 1 times k over 1. Right? Because again, the multiplication will be m times k over 1 times 1. M times k over 1. And similarly, the next one will be 1 over n times 1 over k. So far, I did not break any laws. I just spread all these multiplications into individual pieces. So again, multiplying m times k times 1 times 1 will be m times k here. 1 times 1 times n times k will be here. Great. Now what do we do? Well, very simple. Using the commutative law, I can combine this and this together, and, oh, I'm sorry, this is supposed to be a vertical bar. And again, if you remember, one of the definitions of these rational strings when I introduced this formalism was that any number over 1 times 1 over any number will give 1 over 1. So k over 1 and 1 over k, as it was stated in the definition of these rational string, by definition is 1 over 1, and 1 over 1 multiplied by anything will be 1 over 1. So basically I'm just gathering all the pieces together but in a different order. Same thing, m and 1 times n, so this will be m over n. Which is exactly what we wanted to prove, that this is equal to this. So we can reduce. So using the laws which we have introduced when this formalism was first presented, the laws of what is the unit 1 over 1, what is an inverse number, k over 1 versus 1 over k. All these were in this previous lecture when I introduced these rational strings. So I'm using whatever was defined over there as the laws of transformation, and basically that proves that we can reduce the rational string the same way as you used to think about reducing any rational fraction. So there is nothing new here. However, what is important is that we have established this based on a relatively rigid foundation. Okay, let's move on. Next is addition. So far, I have not talked about operation of addition with rational strings. Well, again, we have to define something, right? And operation of addition is not really defined at all among these rational strings. But I have to define it in such a way that, well, it would be a nice definition which doesn't break any laws, and it corresponds to whatever we intuitively think about addition of rational numbers. You know, this common denominator thing, and etc. So that's what I'm trying to approach right now. Okay, let's start with the point that all integer numbers are well mapped into rational numbers using this mapping. Any integer number corresponds to rational number of this type when the right-hand side, right integer number in this rational string is 1. Now, that means that if we want to build a nice theory which looks reasonable, then m plus n should map into m plus n over 1, right? So m maps to m over 1, n maps to n over 1, and the reasonable definition would be that the sum will map into this particular rational number. So what we actually define right now is the law of addition of certain rational numbers, primarily these two numbers. So instead of corresponding, I will put an equal sign. And this is the definition. So to add two numbers which have the same right denominator equal to 1, I just have to add their nominators, left-hand numbers, and retain 1 on the right-hand side. This is the definition. But now this is just the definition of numbers which have 1 as the denominator. Okay, how can we expand it to something else? Well, do you remember the very nice distributive law among the integer numbers? This is distributive law. Sum times some number is the first of these two times this multiplier plus the second one. So this is called the distributive law among integer numbers. Obviously, I would like to introduce my rational arithmetic in such a way that nice laws which we had in integer numbers will be preserved, like the sum, for instance. So I will try to do the same here. If I have this type of equation, I will multiply both sides by some rational number, and I should actually have this distributive law observed. What it means is the following. If I will multiply both sides by 1 over k, so it will be like this. M over 1 plus n over 1 times 1 over k should be equal if all the laws are correctly defined So I just took this equation and multiplied by, again it should be over, by 1 over k. So if this is true by definition, this should be true if we want our distributive law to be correct, right? And I have to put some extra parentheses around this, right? Okay, now distributive law says that I can multiply the first m over n by this, and that will be what? It will be m over k. So m over 1, according to distributive law, I'm multiplying the first out of these two numbers by the factor, by the multiplier, plus the second one. N over 1 times 1 over k, by the definition of multiplication, is this. So the left part is this. What's the right part? Right part is this, right? M plus n times 1, 1 times k, so it's m plus n. So this is a definition of the addition of two numbers which have the same denominator. So this was a definition for two numbers, addition of two rational strings with 1 as the right-hand side, the denominator. But using the distributive law, we basically expanded this definition into the definition of addition of any two numbers, any two rational strings with the same right-hand denominator. You just add the left-hand sides together and you retain k, k, k. You retain the denominator, the right-hand side. So this is a definition, but definition, not just any definition. I can't put m over k plus n over k equals, for instance, 2m plus 10n over k, because that would not be reasonable. Then the distributive law would not hold. We would like everything to be nicely defined, so our laws of arithmetic, which we used to use, would be held. So that's the right definition. And now there is only one step to define addition of any two numbers. And that's how we will do it. If you remember, we started with the law of reduction. So if we have common multiplier between left and right parts of this number, we can reduce it. What it means is, if I have a over b. If I have to define a over b plus c over d, I can say that this is the same as common denominator, b times d. So, by definition of, by the fact that we have proved the reduction of this thing, I can say that instead of AB, I can put A times D, B times D, because it can be reduced by the multiplier, common multiplier D. So that's the same as A over B. Same thing here. But here I will introduce the common multiplier B. So it will be B times C over B times D. So instead of this, I can write this, because it can be reduced by B. But now, lo and behold, the right-hand sides are the same. So I can use this particular law, where M is A times D, N is B times C, and K is B times D. So it will be A times D plus B times C over BD, which defines operation of addition among rational strings A over B and C over D, which exactly corresponds to your intuitive knowledge about rational numbers and the law of addition by looking for some common denominator. In this case, I just chose B times D, if B is one denominator and D another, and B times D is the common denominator, obviously, and then multiplying correspondingly the left parts, A times D and B times C. Okay, so this is exactly corresponding to our not so rigid, if you wish, definition of the rational numbers. Well, but nevertheless, it's basically a more formal introduction of rational strings, and if people feel the necessity to put this more formal and firm foundation behind the number, just a little bit beyond their intuitive meaning, that's the one. There are others as well. This is just one of the things. Alright, so we have covered addition. Multiplication was done before when we introduced these rational strings. How about division and subtraction? And zero, basically, that's the only thing which remains. Let's start with zero. Rational zero is any number of this type. Z is any integer number, and this is zero. So any rational number with denominator not equal to zero, obviously, but numerator equal to zero, plays the role of zero in rational numbers. How can I prove it? Now, what is zero? Zero is something if you add to any other rational number, result in that other rational number. So let's just add A over B plus 0 over Z. It's equal to common denominator BZ. So it will be AZ A times Z plus 0 times B over B Z equals, well, 0 times B is 0, so it's A times Z over B times Z. Z can be reduced by, which retain results in A over B, as is supposed to be if we are adding 0. So, as I said, 0 over Z plays in this formal rational strings the role of 0. And again, obviously, we all know that in our intuitive rational understanding, 0 over any number 0 in numerator and denominator not equal to 0 is 0. So that basically kind of introduces this number 0 and proves that the concept can be formalized relatively well. Okay, what's remaining? Subtraction and division. Okay, that's simple. Obviously we define these two operations as reverse to their counterparts. So, to subtract A over B, minus C over D, in theory what we have to receive is some kind of a number x over y in such a way that x over y plus C over D would result in A over B. So we have to define it in such a way, this x over z, that this equation holds. Now, from this equation, obviously, it's what? X times d over plus c times y over y times d. Common denominator y times d, x I multiply by d, and c I multiply by y, right? So we have to have this to be equal to A over b. Now, as you understand, we would get exactly the same thing if I would do A over B plus minus C over D equals to X over Y. Because, again, this is an addition. So now we can multiply A times D minus C over minus C times B over BD. So we will basically have transformed this particular equation into the same one which we had before, the same equation between X, D, C, Y, and A and B, which basically proves that to subtract two numbers, we can instead have addition of another number where the numerator just changes the sign. Now, I probably would not do these calculations. They're kind of tedious and obvious. But if you will just use the common denominator in this particular case, you will get exactly the same type of equality for x and y and a, b, c, and d. So that's for subtraction. How about division? Again, very similarly. We will substitute division with multiplication. So in this case, if this is division, what it means? It means basically that x over y times c over d should be equal to a over b. That's what divide actually means, right? So we have to define it in such a way that this is a correct equation, which means now, according to the multiplication, it's x times c over y times d should be equal to a over b. Now, again, if we will change our original equation instead and put a over b multiplied by d over c, I'm reversing. In addition, I had to reverse the sign, in multiplication, I have to reverse numerator and denominator, obviously. Now, that actually should be equal to xy. And again, if you will do all these multiplications, this and this would mean exactly the same thing. So that's the definition of division. Well, we have defined an object, which is a rational string, operations of multiplication and division, with 1 over 1 being a unit for multiplication, which retains the number as it was. We have defined addition and subtraction and the number 0. We have defined an operation of reduction of rational strings. Well, that seems to basically complete the whole thing, except one little detail which I would like to, it's kind of a subtle detail, but still important. We know that numbers, let's say 3/5 and 6/10, are the same because they can be reduced one to each other. Now, among strings, we also talked about reduction. And now, what I believe makes sense is to slightly change our definition of the rational number. Rational number is not just any string of this type where a and b are any integer number. I would actually like to have something like this. I multiply both a and b by the same factor, by the same multiplier. I would like this, which is obviously equal to this one, not to be another rational number which is equal to the first one, but rather to be the same object. So I do not want, in the formalism which we are trying to build, I do not want to consider these to be two different, they are different strings, by the way, but I don't want them to be different rational numbers. I would say that these are the same. So rational number is not just any string of this type, but a set of strings with this property. So a over b, string over b, and a times k over b times k, these are actually representations of the same rational number rather than two different objects which are equal to each other. Again, it's a little subtle, but if I will ask you what's the result of a division one number over another by another, you will tell me, okay, this is that number. But then I will tell, but okay, how about if I will multiply numerator and denominator by 2, let's say? Well, you can say, well, this is the same number, but it's represented differently, right? So that's why I don't want to say that the result of division a over b by c over d is a whole infinite set of different rational strings equal to each other. I'd like to say this is some rational number. So rational number is a whole set of strings, infinite set of strings, which are reducible to each other using the laws of reduction. Yes, I understand this is a little, again, subtle, and it's more of a formal rather than something which will introduce any real need in this theory. But still, I would prefer this to be defined this way, just to have a uniqueness of the rational number. So these are actually the same rational number. Well, that concludes our lecture about arithmetics of the rational numbers. Thank you.